Good morning. Solving linear congruences, which have the form AX is congruent to B mod M, is an essential task in the study of number theory and its applications. To solve linear congruences, we employ inverses modulo M. We explain how to work backwards through steps of the Euclidean algorithm to find inverses modulo M. Once we have found an inverse of A modulo M, we solve the congruence AX is congruent to B modulo M by multiplying both sides of the congruence by this inverse. A linear congruence of the form AX is congruent to B mod M, where M is a positive integer, A and B are integers, and X is a variable, is called a linear congruence. How can we solve the linear congruence AX is congruent to B mod M? That is, how can we find all integer X, that's all integers X that satisfy this congruence? One method that we will describe uses an integer A hat, or the complement of A, such that the complement of A times A is congruent to 1 mod M, if such an integer exists. Such an integer A complement is said to be an inverse of A modulo M. Theorem 1 guarantees that an inverse of A modulo M exists whenever A and M are relatively prime. Theorem 1. If A and M are relatively prime and M is greater than 1, then an inverse of A modulo M exists. Furthermore, this inverse is unique modulo M. That is, there is a unique positive integer complement of A less than M that is an inverse of A modulo M, and every other inverse of A modulo M is congruent to the complement of A modulo M. Example 1. Find an inverse of 3 modulo 7 by first finding Bezout coefficients 3 of 3 and 7. Note that we have already shown that 5 is an inverse of 3 modulo 7 by inspection. Because GCD of 3 and 7 is 1, Theorem 1 tells us that an inverse of 3 modulo 7 exists. The Euclidean algorithm ends quickly when used to find the greatest common divisor of 3 and 7. 7 is equal to 2 times 3 plus 1. From this equation, we see that minus 2 times 3 plus 1 times 7 is equal to 1. This shows us that minus 2 and 1 are Bezout coefficients of 3 and 7. We see that minus 2 is the inverse of 3 modulo 7. Notice that every integer congruent to minus 2 modulo 7 is also an inverse of 3, such as 5, minus 9, 12, and so on. Example 2. Find an inverse 101 modulo 4620. Solution. For completeness, we present all the steps used to compute an inverse of 101 modulo 4620. Only the last step goes beyond methods developed in section 4.3 and illustrated in example 17 in that section. First, we use the Euclidean algorithm to show that the GCD of 101 4620 is equal to 1. Then we will reverse the steps to find the Bezout coefficients A and B such that 101A and plus 4620B is equal to 1. It will then follow that A is an inverse of 101 modulo 4620. The steps used by the Euclidean algorithm to find the GCD of 101 4620 are, and I've used Excel as I have in previous examples to find out that the greatest common divisor is 1. Because the last non-zero remainder is 1, we know that the greatest common divisor of 101 and 4620 is 1. We can now find the Bezout coefficients for 101 and 4620 by working backwards through these steps, expressing GCD of 101 and 4620 equal 1 in terms of each successive pair of remainders. In each step, we eliminate the remainder by expressing it as the linear combination of the divisor and the dividend. We obtain, and I'll just go right here to the last step, minus 35 is the coefficient times 4620 plus 1601 times 101 is equal to 1. That minus 35 times 4620 plus 1601 times 101 equal 1 tells us that minus 35 and 1601 are Bezout coefficients of 4620 and 101, and 1601 is an inverse of 101 modulo 4620. Once we have an inverse A hat, or the complement of A modulo M, we can solve the congruence. AX is congruent, not equal, congruent. We'll have to make this a little addition here. AX is congruent to B modulo N by multiplying both sides of the linear congruence by the complement of A as shown in example 3. Example 3, what are the solutions of the linear congruence 3x is congruent to 4 mod 7? By example 1, we know that minus 2 is an inverse of 3 modulo M. So we multiply both sides, obtaining minus 6x is congruent to minus 8 modulo 7. Because minus 6 is congruent to 1 mod 7 and minus 8 is congruent to 6 mod 7, it follows that if x is a solution, then x is congruent to minus 8 is congruent to minus 8 is congruent to 6 mod 7. We need to determine whether every x with x is congruent to 6 mod 7 is a solution. Assume that x is congruent to 6 mod 7. Then by theorem 5 of section 4.1, it follows that 3x is congruent to 3 times 6 is equal to 18, where 18 is congruent to 4 mod 7, which shows that all such x satisfy the congruence. We conclude that the solutions to the congruence are integers x such that x is congruent to 6 mod 7, namely 6, 13, 20, and minus 1, 8, and 15, and so on. The Chinese remainder theorem. Example 4. In the 1st century, the Chinese mathematician Sun Tzu asked, there are certain things whose number is unknown. When divided by 3, the remainder is 2. When divided by 5, the remainder is 3. When divided by 7, the remainder is 2. What will be the number of things? This puzzle can be translated into the following question. What are the solutions of the systems of congruences? X is congruent to 2 mod 3. I've written this as equalities when they're really congruents here. Please excuse me. And x is congruent to 3 mod 3, and x is congruent to 2 mod 7. We will solve this system, and with it, Sun Tzu's puzzle. Theorem 2, the Chinese remainder theorem. Let M1, M2, all the way out to Mn be pairwise relatively prime, positive integers greater than 1, and A1 through An arbitrary integers. Then the system of congruences, x is congruent to A1 mod M1, x is congruent to A2 mod M2, and so on down to x is congruent to An mod M, has a unique solution modulo M, where M is equal to the product of M1 through Mn. That is, there's a solution with x, there's a solution x with 0 less than or equal to x less than M, and all other solutions are congruent modulo M to this solution. Proof. To establish this theorem, we need to show that a solution exists and that it is unique modulo M. We will show that a solution exists by describing a way to construct this solution. To construct the simultaneous solution, first let M, capital M sub k, be the ratio of M divided by M sub k, for k equal 1 to n. That is, M sub k is the product of the moduli except for M sub k. Because m sub I and m sub k have no common factors greater than 1 when I not equal to k, it follows that the greatest common divisor of little m sub k and big M sub k is 1. Consequently, by theorem 1, we know that there is an integer y sub k, and that the inverse m sub k modulo m sub k, the inverse of capital M sub k modulo small m sub k, such that m sub k, big M sub k, y sub k is congruent to 1 modulo little m sub k. To construct simultaneous solution, form the sum x is equal to a1 big M sub 1 y1 plus a2 big M sub 2 y2 plus all the way on out to an big M sub n y sub n. We will now show that x is a simultaneous solution. First, note that because m sub j is equivalent to 0 mod m sub k whenever j not equal to k, all terms except for the kth term in this sum are congruent to 0 modulo m sub k. Because big M sub k, y sub k is congruent to 1 modulo little m sub k, we see that x is congruent to a sub k modulo little m sub k for k equal 1 to n. We have shown that x is a simultaneous solution to the n congruences. Let's stop there and begin